Greetings, ladies and gentlemen. I welcome you all to our today's lecture. In today's lecture, we shall be talking about what we call the bases and dimensions of a vector space. So to talk about the basis of a vector space, then you need to recall the concept of linearly independent vectors and what we call a spanning set. So we shall be using the two to talk about the basis of a vector space. So, ladies and gentlemen, I encourage all of us to subscribe to this channel. Simply hit the subscription button and you will get timely videos in case they are uploaded. So, let us look at what we call the basis of a vector space. So, to define a basis of a vector space, then we shall talk about two things, as I said. That is the concept about linearly independent vectors and the concept of what we call a spanning set. So let us look at the definition. So if we have a non-empty set S of a given vector space V, we shall be able to call this set S a basis of V if it satisfies two conditions. The first one, that S must be a linearly independent set and every vector in V can be uniquely expressed as a linear combination of elements of S. In other words, this S must be spanning V. So if the two are satisfied, then we shall be able to call that given set a basis of the vector space. We shall be defining the vectors in S as basis vectors. That is, the vectors within a set which we have said is a basis. So we shall be calling them basis vectors. We can look at examples to understand better what we call a basis of a vector space. In other words, in order to prove that a given non-empty set is a vector space, we shall need to prove these two things that we have already looked at. So let us look at examples. Let us look at the first example. It says that show that the following four vectors form a basis of R4. In these vectors, we are given this vector 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, then 0, 0, 0, 1. So we can easily relate these vectors to be, for example, this one here to be our V1, this to be our V2, this one to be our V3, and this one to be our V4. So in order to show that these vectors form a basis, we need to prove two things. One, we must show that they are linearly independent, and two, we must show that they span the vector space which is R4. So that is our major intention. So let us first look at the first case. Let us see whether these vectors are linearly independent. In order to show that they are linearly independent, we shall need to show that when we take the linear combination of these vectors, V1, V2, V3, and V4, then the linear combination will give us 0. That is our major interest. So for that case, we have got our linear combination as alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4 equaling to 0. But what is a 0 in R4? The 0 in R4 is actually 0, 0, 0, 0. So then we already have V1, we already have V2, we already have V3, we already have V4. So we shall put these vectors So this is corresponding to V1, corresponding to V2, this is corresponding to V3, this is corresponding to V4, and of course our 0 vector in R to power 4, 0 vector in R to power 4 is same as the 0 with 4 components. So that is 0, 0, 0, 0. So we shall multiply alpha 1 into this vector, shall be able to get alpha 1, alpha 1, alpha 1. Then here we shall be able to multiply alpha 2 into this, we shall be able to multiply alpha 3 into this, shall be able to multiply alpha 4 into that. So adding the corresponding components, we shall be able to get alpha 1 plus 0 plus 0 plus 0. So it will remain alpha 1. Alpha 1 plus alpha 2 plus 0 plus 0 shall remain with alpha 1 plus alpha 2. Then next, alpha 1, alpha 2, that is alpha 1 plus alpha 2 plus alpha 3 plus 0. So we shall remain with this. So the same, we shall remain with that. So from here, we shall equate the corresponding components because we are saying this vector is equal to that. And for that case, well, it will imply that actually alpha 1 is equal to 0. Then alpha 1 plus alpha 2 will also be equal to 0. Alpha 1 plus alpha 2 is also equal to 0. We have seen that alpha 1 is equal to 0. Also alpha 1 plus alpha 2 plus alpha 3 will be equal to 0. And lastly, we shall have alpha 1 up to alpha 4, that is alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is also equal to 0. So what do we get there? From equation 2, we can substitute for alpha 1, so it will be 0 plus alpha 2 is equal to 0, so it will give us alpha 1 as 0. Similarly, from 3, we have clearly already seen that alpha 1 plus alpha 2 is equal to 0, meaning that where there is alpha 1 plus alpha 2, we can put 0 plus alpha 3. It will also give us 0, so alpha 3 is also equal to 0. So from here, we have seen that alpha 1 plus alpha 2 plus alpha 3 as given in equation 3 is 0, meaning the whole of this is 0. So actually from 4, we can also say that 0 plus alpha 4 is equal to 0. So clearly alpha 4 will be equal to 0. So this implies that alpha 1 is equal to 0, alpha 2 is equal to 0, alpha 3 is equal to 0, and alpha 4 is equal to 0. So clearly it means the linear combination of these vectors here has only one solution when we equate them to 0, and that solution is that alpha 1 is equal to 0, alpha 2 is equal to 0, alpha 3 is equal to 0, and alpha 4 is equal to 0. So if we are able to show that the only solution to our linear combination equated to 0 is alpha or the scalars equaling to 0, then it means that the vectors are linearly independent. Therefore, V1, V2, V3, and V4 are linearly independent vectors. Are linearly independent vectors. So we have shown that the vectors are linearly independent. So we look at another case, which is spanning. So we need to show that these vectors span R4, or they generate R4. So for that case, let us look at the case number 2. In our next case, we need to show that this set here spans R4. In other words, these vectors V1, V2, V3 up to V4 span R4. In order to do that, we shall first of all need to let any vector V, which is of the form X, Y, Z, and W, to be picked from R to power 4. We shall let any vector to be picked from R to power 4, and this vector must be written as a linear combination of these vectors. If we are able to obtain the scalars, in a such a way that we can write this vector as a linear combination of these vectors, then we shall be able to say that this set or these vectors span R4. So let us write. So what we need is, we need to show that alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4, this is equal to v. This one here is equal to v. So we are interested in getting the values of these scalars here. So if we are able to get the values, or the values for these scalars alpha 1, alpha 2, alpha 3, and alpha 4, or if there exists a solution to this expression here, then we shall be able to say that if the solution exists, then we shall be able to say that these vectors here span R4. So let us substitute for our vectors. So we shall have alpha 1 into 1, 1, 1, 1 plus, so we shall add there alpha 2 into v2 plus alpha 3 into v3 plus alpha 4 into v4, and this must be equal to v, which v is an element from R4, which is x, y, z, and w. So simplifying this, when we simplify by multiplying alpha 1 through v1, we shall be able to obtain this. The same way, we shall be able to add the corresponding components. Alpha 1 plus 0 plus 0 plus 0 shall be able to remain with alpha 1 plus alpha 2 plus 0 plus 0, we shall be able to remain with this. So we shall simplify that, and we shall be able to obtain this expression here. So from here we can equate the corresponding components. So equating the corresponding components, so when we do that, we shall be able to equate alpha 1 with x. So we shall be able to obtain alpha 1 is equal to x. And then next we shall have alpha 1 plus alpha 2, which is equal to y. Next we shall have alpha 1 plus alpha 2 plus alpha 3, which is equal to z. Next we shall have alpha 1 plus alpha 2 plus alpha 3 plus alpha 4, which is equal x, y, z, then w. So let us turn to that. So we shall have alpha 1 with x, alpha 1 plus alpha 2 equated to y, alpha 1 plus alpha 2 plus alpha 3 equated to z, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 equated to w. So now we need to obtain the values of the scalars alpha 1, alpha 2, alpha 3, and alpha 4. So if the solution exists, we shall now be able to give the conclusion. So from here, this we can call it equation 1, equation 2, 3, and equation number 4. So from 1 and 2, we can easily see that alpha 1 is x. So it means from 1 and 2, we can say that x plus alpha 2, that is now from 2. X, where there is alpha 1 plus alpha 2 is equal to y. So in other words, our alpha 2 is y minus x. So next, we are given that from 3, we can see that alpha 1 plus alpha 2 is here, but alpha 1 plus alpha 2 is y. So we can write this as y plus alpha 2 is equal to z. So it means this is y plus alpha 3. So where there is alpha 1 plus alpha 2, we are putting y, because y is alpha 1 plus alpha 2. So we shall have y plus alpha 3 is equal to z, and it implies that alpha 3 is z minus y. So we shall have that. Next, when we look at 4, from 4, we can easily see that alpha 1 plus alpha 2 plus alpha 3 is already z. So the whole of this is z. So we can say z plus alpha 4 is equal to w, and alpha 4 will be w minus z. Okay, so clearly we can easily see that we have the values for alpha 1 as x, alpha 2 as y minus x, alpha 3 as z minus y, and alpha 4 as w minus z. So clearly we can easily see that for any vector from r to power 4, for any vector from r to power 4, we are able to get the scalars, that is alpha 1, alpha 2, alpha 3, and alpha 4, because these will be defined values. These will be real numbers. So if these are real numbers, then clearly it means we can obtain alpha 1 if x is known. We can obtain alpha 2 if y and x are known. We can obtain alpha 3 if z and y are known. We can obtain alpha 4 if w and z are known. In other words, if v is known, which v is the x, y, z, w, if this v is known and v is an element of r to power 4, then we are able to write the linear combination of this one equaling to v, or we are able to express v in terms of linear combination of these vectors v1, v2, v3, and v4. But in case the solution if the solution could not exist, then it means this v would not be written as a linear combination of v1, v2, and v3. So for that case, if we are able to obtain the values of alpha 1, alpha 2, and alpha 3 plus alpha 4, then clearly the vectors v1, v2, v3, and v4 will be spanning R4. So this will imply that we are able to write alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4 equaling to our vector v, because you already know v, and this v here you already know alpha 1, and this alpha 1 is x, so you can easily write x v1 plus y minus x into v2 plus z minus y into v3 plus w minus z into v4, and this is equaling to x, y, z, and w. So you can write this as a linear combination of the vectors v1, v2, v3, and v4. So we shall give our conclusion that this implies that therefore this set here, so we give our conclusion that this set of the vectors v1, v2, v3, and v4 spans R4. So these vectors here span R4. So if that is the case, now let us now give the general conclusion that therefore the set, the set, which set is containing v1, v2, v3, and v4, this set here is a basis of R to power 4, because it has satisfied all the two conditions for which any given set is supposed to be a basis of R4. That is, they are linearly independent, these vectors are linearly independent, and we have seen that this set here spans what we call R4. So if the two conditions are satisfied, then we give our conclusion that this set is a basis of R to power 4. We look look at example number 2. In example number 2, we need to determine whether the vectors 1, 1, 1, 1, 2, 3, and 2, negative 1, 1 form a basis of R3. In order to do that, we shall need to prove that these vectors here are 1, linearly independent, and 2, they span what we call R3. So let us consider B to be our set, which is containing V1, V2, and V3. So in other words, we have our B, which is a set of vectors V1, V2, and V3. So for the first case, we shall need to show that this set here is a linearly independent set. And to show that, we have to set the linear combination to what we call 0. So that is why we have alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 equaling to 0. And for that case, we shall substitute for alpha V1, V2, and V3. And a 0 in R to power 3 is actually a set having a 0, 0, 0. So that is a vector 0, 0, 0 with 3 components. So for that case, let us substitute for V1, V2, and V3. So we shall have alpha 1 into 1, 1, 1, alpha 2 into 1, 2, 3, alpha 3 into 2, negative 1, and 1 equaling to 0, 0, 0. So for that case, we shall multiply this alpha 1. That is alpha 1, that is alpha 1, that is alpha 1. This is alpha 2, 2 alpha 2, 3 alpha 2. This is 2 alpha 3 minus alpha 3. Then this will be alpha 3 equaling to 0, 0. We shall add the corresponding components, alpha 1. So we shall have alpha 1 plus this alpha 2 plus 2 alpha 3, 2 alpha 3. So the corresponding components. This one corresponds to this. So we shall have alpha 1 plus 2 alpha 2 plus, it corresponds to this, negative alpha 3. Next, we shall have alpha 1 corresponds to this. So alpha 1 plus 3 alpha 2 plus this is alpha 3. This is equal to 0, 0, 0. So that is what we shall have. So we shall equate the corresponding components. So equating the corresponding components, we shall have. So equating the corresponding components, we shall be able to obtain alpha 1 plus alpha 2 plus 2 alpha 3 equaling to 0, this one equaling to 0, and this one also equaling to 0. And for that case, we shall be able to obtain these three equations. So we need to solve and find the values of alpha 1, alpha 2, and alpha 3 given the three equations. So for that case, we shall form an augmented matrix. So this becomes our augmented matrix. So we shall use row operations to obtain the echelon form. So for that case, we can apply the operation negative R1 plus R2 to give us R2, negative R1 plus R3 to give us R3. So if we do that, we shall be able to obtain R1 is constant, 1, 1, 2. So we shall have this as 0. So negative 1 plus 1, it will give us 0. So negative 1 plus 2, it will give us 1. We are saying negative 1 plus this value here, which is 2. So we shall be able to get 1. So next we shall have negative of this, that is negative of 2. Negative of 2 plus R2 we have negative of 1. So this will give us negative of 3. So we shall have negative 3 here, and this will remain 0. So next, negative of row 1, negative of 1 plus 1, it will give us 0. Negative of 1 plus 3, negative of 1 plus 3, it will give us a 2. So we shall have 2 here. Then negative of 2 plus 1, negative of 2 plus 1, it will give us negative of 1. So we shall have negative of 1 here, then this will be 0. So our next operation will be to eliminate this. So it means we shall put negative of 2 in row 2. We add there row 3 to get row 3. So that will give us the same matrix maintained 1, 1, 2, and this will be 0, 0, 1, negative 3. This will be 0, and this will remain 0. So it means we shall apply negative 2 here. So minus 2 times 1 plus 2 will give us also 0. So we shall have minus 2 times minus 3, but adding there negative 1. So this will be 6 minus 1, and this will give us 5. So we shall have a 5 there, and this is 0. So for that case, we need also to create a 1 here. So we can put 1 over 5 in row 3 to give us row 3. So we already have 1 there. So we shall have 1, 1, 2, then 0. This is 0, 1, negative 3, and 0. So this will be 0, 0, 1, and this will be 0. So we can get the corresponding linear system. We have already put it in our echelon form. Let us get the corresponding linear system. So the corresponding linear system will be alpha 3 equaling to 0, then alpha 2 minus 3 alpha 3 equaling to 0, then plus that one there. So we shall be able to have alpha 1 plus alpha 2 plus 2 alpha 3 equaling to 0. That is per the first row. Alpha 1 plus alpha 2 plus 2 alpha 3 equaling to 0. So we shall be able to obtain this. Then the next one will be alpha 2 minus 3 alpha 3 is equal to 0, and alpha 3 is equal to 0. So for that case, we already have alpha 3 equaling to 0. So from, you can call this one 1 and this one 2. So from equation 2, using back substitution, we can get alpha 2 minus 3 times 0 is equal to 0. Of course, this will give us alpha 2 equaling to 0. So next, we shall look at equation number 1 from equation 1. So we shall be able to say that alpha 1 plus 0 plus 2 times 0 is equal to 0. So alpha 1 will be equal to 0. So clearly, we have got alpha 1 as 0, alpha 2 as 0, and alpha 3 as 0. So when we are able to get the only solution to be the only solution of the scalars to be 0, then we shall be able to conclude that the vectors are linearly independent. So according to what we have our vectors v1, v2, and v3. And we have seen the only solution to the linear combination here is only alphas equaling to 0. So we shall give the conclusion that since alpha 1 is equal to 0, alpha 2 is equal to 0, and alpha 3 is equal to 0, is the only solution to the linear combination, that is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equaling to 0. If it is the only solution to this, is the only solution for this, then it implies that v1, v2, and v3 are linearly independent vectors. These ones are linearly independent vectors. And for that case, it means our set V, which is our set B, which is containing these ones here, is a linearly independent set. So you can also say it implies that the B, which is the set that we had read, V1, V2, and V3 this one here is a linearly independent set. So this one is a linearly independent set. So first case is proved. So we can look at another case where we need to show that this set here spans R3. In case 2, we need to show that B, which is having vectors v1, v2, and v3, spans R3. And in order to show that, we must pick a vector in R3, and that vector must be expressed as a linear combination of vectors v1, v2, and v3. Or you can say that every vector that you pick from R3 must be expressed as a linear combination of these vectors here. But in order to do that, then we have to pick one vector which is an arbitrary vector in R3, and we see whether we can write that vector as a linear combination of these vectors. So let us pick or get the vector v, which is of the form x, y, and z in R3. Then our interest is to express this v as a linear combination of v1, v2, and v3. So we shall do that as we have done in our expression here. So we already have v1, v2, v3, and v. So we shall substitute them and try to simplify. So when we simplify this, we shall be able to get this expression, which will give us 3 equations, that is upon equating the corresponding components. So when you equate the corresponding components, you will be able to get these 3 equations, which you can put in the augmented form. And in augmented form, we shall have 1, 1, 2x, 1, 2, negative 1y, then 1, 3, and 1, then and z. So in augmented form, we shall be able to get this matrix here. So our interest is to simplify this matrix in echelon form, so we can see if the solution exists or not. So let us look at how best we can deal with this matrix. So looking at this matrix here, let us try to create a 0 here and here using operations. We can say that is negative R1 plus R2 to give us R2, then negative R1 plus R3 to give us R3. So when we do that, we shall be able to get, so we shall be able to maintain this first row constant. Then we shall apply our operations in row 1 and in row 2 and row 3. So of course we shall be able to obtain this matrix. So that is, you are applying negative 1 in this one. So that is negative 1 plus 1, that is 0. Negative 1 plus 2, you will get 2 minus 1, which is 1. Negative 2 plus negative 1 will give you negative 3. Negative x plus y, that will be y minus x. So looking at this, negative 1 plus 1 is 0. Negative 1 plus 3 is 2. Negative 2 plus 1 is negative 1. Then negative x plus z will give us z minus x. So we shall obtain this matrix. So let us also try to eliminate these 2 using another operation. So using this operation, negative 2 in row 2 plus row 3 to give us row 3. So we shall be able to have here, the first row is constant, 1, 1, 2. Then we shall have x here. Then this is 0, 1, negative 3. This is y minus x. Then the next one will be, of course, this will remain 0. Then negative 2 times 1 is negative 2 plus 2 will give us 0. We are having negative 2 times negative 3 plus negative 1. This will be 6 minus 1, which is 5. So next we shall be having a negative 2 multiplied in this, that is negative 2 multiplied in y minus x, but we shall need to add there R3, which is z minus x. Z minus x. So this will give us negative 2y plus 2x plus z minus x. Okay, so this will give us negative 2y, and this one with this will give us x. So in other words, we shall have z plus x minus 2y. So this is what we shall have here, z plus x minus 2y. So that is what we have obtained there. So in that case, we can also try to create a 1 here. So that is applying 1 over 5 in row 3 to give us row 3. And that will be 1, 1, 2, 0, 1, negative 3, 0, 0. It means this will be 1. And here we are remaining with x. This is y minus x. Then this will be 1 upon 5 of z plus x minus 2y. So this is what we shall obtain. So from here we can get the corresponding linear system. We shall now obtain the corresponding linear system as alpha 1 plus alpha 2 plus 2 alpha 3, of course equaling to x, then alpha 2 minus 3 alpha 3 equaling to y minus x. Then this will be alpha 3 equaling to 1 upon 5 into z plus x minus 2y. So we need to deduce the values of alpha 1, alpha 2, and alpha 3. So for that case, we have got these 3 equations, and we are interested in obtaining the values for alpha 1, alpha 2, and alpha 3. So from equation 2, from 2 we can substitute for alpha 3. In other words, from 2 we can say alpha 2 is same as 3 alpha 3 plus, when we bring this one this side, plus y minus x. So we already have alpha 3, so this is 3 times 1 upon 5 into z plus x minus 2y. But we are also adding there y minus x. So we can obtain the LCM here, which will be 5. So this will be 3z. This times this will be 3x. This times this will be minus 6y plus, so we shall multiply the 5 here. 5 divided by 1, we shall get 5 times this. So this is 5y minus 5x. So this will give us, let us try to simplify this. So after simplifying, we shall have 3z. Then this one minus 6y plus 5y will give us minus y, which is this. Then 3x minus 5x will give us minus 2x divided by 5. So this will be same as 1 upon 5 into 3z minus y minus 2x. So this is alpha 2. So we have obtained alpha 2. We can now go on and obtain alpha 3. So from equation number 1, we can be in position to obtain alpha 1. So we have already got our alpha 2 and we already have our alpha 3. So from this we can make alpha 1 the subject, and we shall have it as x minus alpha 2 minus 2 alpha 3. So when we do that, we already have alpha 1, we already have alpha 2 and alpha 3. So substituting for alpha 2, which is this, this is our alpha 2, 3z minus y minus 2x divided by 5. Then minus 2 times alpha 3, which is z plus x minus 2y divided by 5. So from there we shall get our LCM, which will be 5. 5 divided by 1 here, we shall get 5x here. Then this will be minus of 3z minus y minus 2x. Then this will be minus 2 into z plus x minus 2y. So we shall be able to simplify this. This will be 5x minus 3z plus y. This will be plus 2x. Then this will be minus 2z minus 2x. Then plus 4y. Everything divided by 5. So we shall have this as we simplify this. So this will be 5x plus 2x minus 2x. So when we get 5x plus 2x, that will be 7x minus 2x, it will be 5x. So this and this, of course, will cancel, will remain with 5x. Then this is minus 3z. This is minus 2z. So this will give us minus 5z. Then next, we remain with y. This is y plus 4y. Y plus 4y will give us 5y. Everything is divided by 5. So of course this will give us x minus z plus. So on simplifying this, we shall be able to obtain 5x minus 5z plus 5y divided by 5, which will be giving us x minus z plus y. So we have got the value of alpha as x plus y minus z. We have got the value of alpha 3. We have got the value of alpha 2. So clearly, the solution to our linear combination exists. And if that is the case, we can clearly say that the solution of alpha 1, alpha 2, and alpha 3 exists, and therefore we can write alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equaling to v. And if that is possible, then it means that v1, v2, v3, all this set here spans R3. So clearly the two conditions will be satisfied, and if they are satisfied, then we shall give a conclusion that therefore B, which was the set containing v1, v2, and v3, is actually a basis of R3. Is a basis of R3. Determine whether these vectors here form a basis of R3. So as we have seen in our previous two examples, we shall need to prove two cases. That is, one, we need to show that these vectors here are linearly independent, and also these vectors here span R3. So let us begin with the first one. We need to show that these vectors here are linearly independent. And for that case, we shall first of all let B to be a set having these vectors, and we are calling this one v1, v2, and this one v3. So in order to show that B is a linearly independent set, we need to make the combination or the linear combination and equate it to 0. So if we get the values for alpha 1, alpha 2, and alpha 3 all equaling to 0, or if only one solution exists for this expression, and the only solution is the scalars equaling to 0, then we conclude that they are linearly independent. So we have v1, v2, v3, so we shall substitute. So alpha 1 into v1 plus alpha 2 into v2 plus alpha 3 into v3, and the 0 component in R3 is 0, 0, 0. So for that case, you will try to simplify this and as well equate the corresponding components. So when you simplify This one here, you'll be able to obtain this expression. When you equate the corresponding components, it means this will be equal to 0, this expression will be equal to 0, this expression will be equal to 0. So for that case, let us equate the corresponding components. So when we do that, we shall be able to get these three equations. So from these three equations, let us try to solve these three equations here and see what basically it will give us for the values of alpha 1, alpha 2, and alpha 3. So we can form the augmented matrix. So the augmented matrix is so we shall have this as 1, 1, 5. So this will be 0, this will be 1, 2, this will be 3, this will be 0, this will be 2, 5, 4, and this will be 0. So let us use row operations and try to make what we call an echelon form. So we can row 1 and row 2, that is negative row 1 plus row 2 to give us row 2. And also we can put another operation which is negative 2 in row 1 plus row 3 to give us row 3. If we do that, we shall be able to obtain the matrix. So this is remaining constant 1, 1, 5, and this will be 0. So this one here we shall have negative 1 plus 1, that is 0. Negative 1 plus 2, that will be 1. Then this is negative 5 plus 3, that will be negative 2. And this is 0 plus 0, which will remain 0. So next we shall have negative 2 times 1 plus 2, it will give us 0. Negative 2 times 1 plus 5, that will give us 3. Negative 2 plus 5. So negative 2 times 1, that is negative 2, plus this 5, it will give us 3. Then negative 2 times 5, that is negative 2 times 5, it will give us negative 10. Then plus 4, it will remain as negative 6, and this one will be 0. So from there, we can easily, from here we can now easily eliminate this one as well. So we apply negative 3 in row 2 plus row 3 to give us row 3. When we do that, we shall be able to maintain these rows constant. Then also row 2 will be maintained constant. Then we apply the operation, then it will be 0. So because that is negative 3 times 0 plus 0, it will be 0. Negative 3 times 1 plus 3, it will give us 0 as well, because you have negative 3 times 1 plus 3, it will give you 0. Then negative 3 times negative 2, then plus negative 6. So this will be positive 6 minus 6, that will give us 0. And of course, this one is also 0. So looking at this, we can see it implies this system here has infinitely many solutions, because when we get the corresponding linear system, the corresponding linear system will be alpha 1 plus alpha 2 plus 5 alpha 3 equaling to 0. Then this one here will be alpha 2 minus 2 alpha 3 equaling to 0. So clearly we can easily see that we can now set alpha 3, because we have a free parameter, our free variable is alpha 3, because you realize we have two equations but we have three unknowns. So we have a free variable. So alpha 3 is our free variable. So if that is the case, to get the solution, we shall set maybe alpha 3 to be like a parameter t, for t which is an element from R. So that is our t. So after setting alpha 3 to t, it means from equation 2, this is equation 1 and 2. So from 2, it implies that alpha 2 will be same as 2 alpha 3, and for that case, it means alpha 2 is same as 2t. So this will be alpha 2. So to get alpha 1, so from equation 1, we can obtain the value of alpha 1. So we have alpha 2, we have alpha 3. So let us substitute in equation number 1, which is alpha 1 plus alpha 2 plus 5 alpha 3. So from equation 1, we can say this is alpha 1 plus alpha 2. Alpha 2 is 2t. This is plus 2t plus 5t, which is equal to 0. So alpha 1 plus 7t will be equal to 0, meaning that alpha 1 is same as negative 7t. So it is clear that alpha 1 is negative 7t, alpha 2 is 2t, and alpha 3 is actually same as t. So remember, t is any parameter which is any value from a set of real numbers. So it implies that our system has infinitely many solutions. So clearly we can say that alpha 1, alpha 2, and alpha 3, these ones here, have infinitely many solutions. Have infinitely many solutions. Have infinitely many solutions for t, which is an element from R. So for any value of t, you'll be able to get alpha 1, alpha 2, and alpha 3. And this implies that alpha 1 equaling to 0, alpha 2 equaling to 0, and alpha 3 equaling to 0 is not the only solution. So clearly this means, it means alpha 1 equaling to 0, alpha 2 equaling to 0, and alpha 3 equaling to 0. That is when you take t. This one here is when you take t equaling to 0. Is not the only solution. Is not the only solution. Is not the only. Is not the only solution. Is not the only solution. And that implies that this system here, or our vectors, are linearly dependent. Because if they are linearly independent, then the only solution must be alpha 1 equaling to 0, alpha 2 equaling to 0, and alpha 3 equaling to 0. But we have seen that this alpha 1, alpha 2, and alpha 3 has infinitely many solutions, which means alpha 1 equaling to 0, alpha 2 equaling to 0, and alpha 3 equaling to 0 for t. That is in case you take for t, that is for the case of for t equaling to 0, is not the only solution. So if that is the case, then we can give the conclusion that thus v1, v2, and v3 are actually linearly dependent. Linearly dependent vectors. So if they are linearly dependent vectors, of course we shall not be able to get a basis, because this implies they are not linearly independent. They are not linearly independent. So clearly, having seen that our vectors are linearly dependent, then we shall give a conclusion that B, which contains vectors v1, v2, and v3, is actually not a basis of R3 because one of the conditions is already not satisfying. So if one of the conditions is already not satisfying, then we can give our conclusion that this set, which is containing vectors v1, v2, v3, is actually not a basis of R3. So that is basically how we prove that a given set forms a basis of a given vector space. So you will be able to try some few examples here. So there are some few examples here that you need to try out. And these are, so we have some of the trial questions here. So you need to go through them and try to solve and see whether you are able to prove that these given sets here form a basis for the given vector space. So use the ideas that we have so far looked at. So basically you need to be proving that a given set satisfies the two conditions, that is, that set is linearly independent and also it spans the vector space. If the two conditions are satisfied, then you conclude that that given non-empty set is actually a basis of the vector space. If one of the conditions fails, then you'll be able to give your conclusion that that set does not form or is not a basis of a given vector space. So we shall stop here for today, and of course in our next class or lecture we shall be talking about dimension of a vector space.
Yeah.